Welcome to another Forge College Explainer. If you've been following our track from EVM to SVM, transitioning from Ethereum to Solana, you know we just wrapped up implications for optimization and next steps. Well, today we are transitioning from pure theory to the part that actually, hurts, your wallet. Our focus today, compute unit basics and Solana cost models. Let's get right into the actual billing mechanics of the Solana network.
Here is our roadmap for today. First, we'll go from optimization to billing. 2, the cloud function analogy. 3, compute units, or the meter. 4, priority fees and scheduling. 5, rent, which covers persistent storage. And finally, number 6, we'll put it all together. Let's dive in.
Section 1. From optimization to billing, where does the time and cost actually concentrate?
So before we start measuring anything, let's connect those code optimizations we've been talking about to the billing levers that actually affect your bottom line. Coming from Ethereum, you're used to gas, where literally every single opcode has a very specific price tag attached to it. Well, Solana approaches this totally differently. Understanding this shift is absolutely crucial for writing highly optimized programs without, frankly, going bankrupt. Okay, Section 2, the cloud function analogy, serverless on the blockchain. To make this super intuitive, we're going to treat a Solana transaction exactly like a short run-in serverless cloud function. The mapping is actually uncanny. Think about it. When you run a cloud function like AWS Lambda, you pay for CPU time. On Solana, the equivalent is compute units. When your cloud function spins up, you hit that cold start overhead, right? On Solana, that's your serialization and signature verification. Now, what if you need your cloud job to skip the queue? You pay for a VIP scheduler lane. The Solana version, priority fees. And finally, if your function leaves data behind, you pay for build storage. On Solana, that persistent storage cost is called rent. Keep this blueprint in mind because it honestly makes the whole system so much easier to digest. Moving on to Section 3, compute units, the meter. Let's look at those transient execution costs. Let's start with transient compute. This is really where the execution costs of your actual code starts racking up. A compute unit is basically a metered measure of program execution and runtime overhead. Validators use it to track exactly how much work is done on a transaction. You can think of compute units like a ticking meter in a taxi. You start with a budget, and every single operation, whether it's processing instructions or doing runtime bookkeeping like borrow checks and account locks, it all decrements your budget. If that meter hits 0 before your transaction finishes, well, the validator aborts the execution, the transaction fails, and no, you absolutely do not get a refund for the compute you just burned. So the million-dollar question is, what drains that meter the fastest? Enter the cross-program invocation, or CPI. This happens when your parent program suspends its own execution, and the runtime actually steps in to perform bookkeeping so it can invoke a completely different program. You've got to keep a really close eye on CPIs. Jumping between programs requires extra frame setup, parameter validation, parsing, the whole shebang. All of that heavy lifting chews through your transient compute budget insanely fast. It's an absolutely necessary tool, for sure, but one you have to use deliberately. Section 4, priority fees and scheduling. Let's talk about bribing the bouncer. Okay, so what happens when you need your transaction processed immediately, and you literally cannot afford to wait in line? That's exactly where the priority fee comes into play. It's an optional fee you pay directly to validators just to prioritize your transaction's inclusion in the very next block. Think of it exactly like slipping a 20 to the bouncer for the fast lane at a crowded club. Paying it doesn't reduce the number of compute units you're going to burn once you get inside, but it drastically improves your chances of actually getting in. It gets you through the door when the network is totally jammed. But what if your transaction is just fundamentally massive? Well, by default, Solana caps the amount of compute a single transaction can actually use. If you know you're going to blow past that default, you absolutely have to use a compute budget instruction. This is an explicit in-transaction request directly to the runtime to raise your maximum compute allowance. And here's how it all connects. If you're asking the network to let you run a massive transaction, you almost always pair this instruction with a priority fee. You're basically saying, hey, validator, I know this is a really heavy load, so here's a nice little tip to encourage you to accept it. And this really brilliantly illustrates how all of this surfaces when you're actually debugging. This table is your master blueprint. It shows exactly what each component measures and where you'll find it when you're staring at RPC responses or a block explorer. Compute units measure execution time and show up as compute units consumed. Priority fees are your inclusion bribe and show up right in your transaction fee breakdown. Rent measures that persistent storage and is reflected in your rent-exempt balance. And serialization That measures network overhead, showing up as the raw transaction size in bytes. Seriously, this table is going to be your best friend when we start profiling real transactions in our next lesson. All right, Section 5, Rent. Persistent storage costs. Time to pay the Solana landlord. Let's shift gears from those fleeting, transient execution costs to persistent storage. On Solana, if you want your data to live on the blockchain forever, you literally have to pay for the space it takes up. We call this the rent-exempt minimum. It's the absolute minimum balance of LAM ports an account must hold just to stay alive on-chain without being purged by validators. But here is the kicker. Unlike compute units, which are permanently burned into the ether, rent is actually a deposit. You deposit that minimum balance, which scales proportionally to your exact data size to keep the account alive. And the best part? If you ever close that account and delete the data, the Solana landlord gives your deposit right back.
Section 6. Putting it all together. Let's assemble the machine.
Let's pull this whole engine together and walk through the actual mechanics of a concrete multi-instruction transaction, right? Starting with step 1, before your code even really runs, the runtime charges cold start overhead for deserialization and signature verification. Once you're safely through the door, step 2 hits. Say you do a really simple LAM port transfer. This is incredibly light on compute, but it does touch state, which means the runtime pauses to ensure no accounts accidentally drop below their rent-exempt minimum. Finally, step 3, you hit the heavy compute. Maybe a cross-program invocation to a token program to mint some new tokens. As we discussed, this requires suspending a program, passing contexts, and doing some pretty heavy bookkeeping. So when your boss taps you on the shoulder and asks, hey, how much does this transaction cost? You can't just point to a single number. To find your total economic impact, you always have to sum these 3 distinct layers together. Your total cost is your transient execution burn, those are your compute units, plus any priority fee bribes you paid to the scheduler, plus any persistent storage deposits, your rent, required to open up new accounts, the whole package. And this brings us to the most practical part of today's explainer, how to actually triage your optimization efforts. The absolute key takeaway here is separating your optimization strategy. If you have high compute units, go in there and optimize your hot execution paths. If you're seeing high startup overhead, try to batch your work into fewer transactions. If your transactions are dropping or pending forever, you need to adjust those priority fees. And finally, and honestly, this is a huge one, if your overall total cost is just too high, don't waste 3 weeks tweaking minor code loops. Actually, scratch that. Your real problem might just be a bloated rent exemption requirement. That means you need to fundamentally redesign your account layout to just store less data. I really want you to keep this mental model of the cloud function running in the back of your head. The very next time you see a massive compute unit consumption value, pause and ask yourself, is this purely a transient execution cost? Is it scheduler related? Or is it being caused by repeated serialization overhead because my transactions are structured poorly? Taking 2 seconds to answer that question will literally save you hours, if not days, of misdirected engineering time. And that sets us up absolutely perfectly for our next step in the track, measuring compute units and real transaction costs, or we're going to get our hands dirty with live data. Thanks so much for joining me for this Forge College explainer. Make sure to visit forge.college for tons more great Web3 resources. But before you close out, I want you to think about your own smart contracts for a second. If you were forced to cut your current transaction costs in half by tomorrow, would you rewrite your logic, or would you redesign your data storage? Let that sink in, and we'll see you in the next lesson.